Hi everyone, in this video we're going to see some examples for section 6.1. So a lot of this 6.1 class note problems will be operational problems where we're just going to remember some of the big properties of sets. So let's start with using like rooster notation and set builder notation. So first we have this set here that says all the x belongs to the integers, so that this is between -2 and 5. If we're going to use set rooster, that means that we're going to make a list of the elements that belongs in here. Notice that they're integers, and they're integers between -2 and 5, but they're not including either -2 or 5. So we're going to go with -1, 0, 1, 2, 3, and 4. So that's all the elements that belongs to the set. Now we have the x that belongs to the naturals, where x is even and x is less than 10. So once again, since it belongs to the naturals, it start at 1. But since it's even, then it's going to start at 2. Then the next even is going to be 4, 6, 8. And because we're not including 10, then it's going to close in here. Now, C is x equals 3k for some integer k. And x is an integer, right? And it's between 0 and 15. Notice that we are including 0 and 15. Is 0 a multiple of 3? Yes, we can see it as 3 times 0. So 0 is going to be included. We also have 3, which is 3 by 1. We have 6. We have 9. We have 12. And of course, 15. So this gives me all the possible numbers between 0 and 15 that are multiples of 3 in integers. Now, let's go to set builder notation. So builder notation is about writing a list of elements in terms of a property. So for example, we have here 2, 4, 6, 8, and 10. We can think of this as integers, so that x is equals to k for k bigger or equals than 1. And we can say k is an integer as well. Okay, and so that's going to summarize all the possible even integers. Now we have here multiples of 3, but notice that they're going in any direction. So we can think of this as the x belongs to C, so that x is 3 times L, where L is any integer. And so that's going to give me all the possible integers multiple of 3. Now this says all the real numbers between -5 and 5, including not including -5 or 5. So this is interval notation. So we'll say the x belongs to the real number, so that x is bigger than -5 and less than 5. This is interval notation. This means the open interval -5 to 5. Now let's go to analyze properties like subset and in other operations like intersection, difference, union. So first we have this set A equals 1, 2, 3, 4, 5. B is 2, 4, 6. C is 3, 4, 5, 6. And we're going to check if each of the following statements are true or false. So we first says B is a subset of A. And you can see that that is false because 6 belongs to B, but 6 is not on A. So that's going to make it so B is not an A. C is a subset of A. C is 3, 4, 5, 6. Again, same issue. This has 6. All the other numbers, they're there, but 6, 6 is not. So 6 belongs to C, but 6 does not belongs to A. B is a subset of C. So 2, 4, 6 and 3, 4, 5, 6. This is also going to be false because notice that we have elements in B. Like for example, 2. 2 belongs to B, but 2 is not in C. So it's not a subset. They only have one element in common, which is C. Now it says the subset of 2, 4 is a subset of B. And this is actually true. You can see it. 2 and 4 are elements in B. So every element in 2, 4 is an element in B. So this is true. Now the empty set is a subset of A. And this is going to be true because the empty set is in any set. Okay? The empty set is a subset of A for any A. All right, so now let's go to question number 4. We have here a couple sets. The universe, we have a universe contextual set. We have the set A from 1, 2, 3, 4, 5. We have B 3, 4, 5, 6, 7. And we're going to find some of the following sets. First, the union. And so remember the union, we're just pretty much going to join the list of elements that we have in each of the things. So we have 1, 2, 3, 4, 5. And then here we have 3, 4, 5. We're adding 6 and 7. So that's going to be A union B. That's what this is adding the elements that are not common. Now, the intersection then is only going to be the common elements, and you can see that they have in common 3, 4, 5. Scheme a little bit broken. So 3, 4, and 5. A minus B, per definition, is the elements that are in A that are not in B. So the elements that are in A that are not in B is pretty much 1 and 2. Since 1 and 2 are here, but they're not here. Now, B minus A is the opposite. What are the elements that are in B that are not in A? And then you'll get that is 6 and 7, since they're not common. So we're removing, remember the difference is we're removing the intersection. So we're just only leaving the elements that are proper to each of these sets. A complement. Notice that A is 1, 2, 3, 4, 5. So to reach the universe, we will need 6, 7, 8, 9, and 10. And that is precisely what's going to be the complement set. Now, A union B complement. So we have for A union B, we have this before. So A union B complement is how much am I missing with A union B to reach the universe? Notice this is 1, 2, 3, 4, 5, 6, 7. So we're missing 8, 9, and 10. Okay, hopefully that makes it easier to see the operations. Now let's go to a Cartesian operation. So if we have the set C of AB and the set D of 1, 2, 3, we want to find C times D. And remember, the Cartesian product is just order pairs. So we're going to have A1, A2, A3. It's a pair with the element of A and an element of C and an element of D. And then now we go for the second element, B, B1, B2, B3. So we just created pairs out of all the possible. Now we do D times C is going to be the opposite. The first entry is just going to be the number. So we're going to have 1A, 1B. And then we're going to have 2A, 2V. And then we're going to have 3A, 3B. Notice that this is different from this because the order matters on the pairs. The order pairs, the order matter. So it's going to be quite different. Now, so C times C is C paired with itself. And so that's going to give me pairs AA, AB, and of course, BB. And also going to have BA. Now here, how many elements are in CD? This is about cardinality. We're counting elements, so you can see that it's 6 elements because each of the pairs is 1 element. Is A1 in C times D? And you can see that it is here in the list. So true. Is 1A in CD? This is false. 1A belongs to D times C. And this is just to stress out that C times D is very different from D times C. The order pair structure doesn't make it so they can be similar elements. Now let's go to examples of power set. Remember, the power set of a set is all the possible subsets that we can have for a particular set. So if we have only a set with one element, then you're going to have the empty set, and then you're going to have the set itself. And remember that the rule for the power set is the cardinality of the power of A is twice to the power of the cardinality of A, or the number of elements. Okay? So you can also see this as the number of A. Now, for parts of 1, 2, notice we always have the empty set immediately. We have one set with each of the individual subsets. So 1, 2, and then 1, 2, because the set itself gotta be in there. Every subset is a subset of itself. For parts of the empty set, that's just going to be, so the empty set has no elements. It has 0 elements. So 2 power to the 0 is just going to be 1 element. And you can kind of guess which one is going to be, which is the empty set. Now, this is asking how many elements parts of ABC or power of ABC have. And of course, according to this rule, because ABC has 3 elements, so the cardinality of this is 3 elements. So parts of ABC cardinality is going to be 2 to the 3, which will be 8. Okay, so now question number 7 is we have some intervals. We have, as a context, use the real line. And now we have 2 intervals. We have the interval -2 to 5, and we have the interval 3 to 8. We want to find each of the following and express in interval notation. So A union B. So let's make a line, and let's put the numbers into perspective. So we're going to get -2 here, and then the first element that's going to show up is going to be 3. Then we're going to have 5, and then we're going to have 8. So if we go coloring down, what are the elements? You can see that -2 to 5 is here. And then you have that 3 to 8 is here. So what is this union? Well, this union is clearly -2 up to 8. We're not including the extremes, of course, because this is an open interval. Now, A inter B is something that we can look in the same way. So once again, -2, 3, 5, and 8. And so you can see that here we have -2 to 5. And now in the opposite direction, we have 3 to 8. And so the intersection is where the common elements, and you can see that it's from 3 to 5 that is common. So we have 3 close, 5 close. Now, A minus B is going to be the elements that are in A, but they're not in B. So you can see that pretty much we're removing the intersection. So A minus B, using this same graph here, is just going to be -2 up to 3, but open, because we cannot have the 3 from B. This is A minus B. Now, B complement is what is the rest, which is outside of -3A. So here for B complement, we just need 3, 8 as a set. And we're just going to shade the complement. So 3 to 8 is this. And so the complement is just going to be anything that is outside. So this will be -infinity to 3, and then not included 3, union, and then now we're going to include A because A is not included in B, 8 infinity. That'll be the complement for this. Now, for question 8, we have defined the set M and N as follows. We have M is equals N for K, and N is equals M equals to J for some J. So notice that we're essentially looking for m is multiples of 4. And so we're talking about integers, of course. It's worth mentioning. So this is integers, multiples of 4. And then n is integers multiple of 2. Okay. Now we want to say, is m a subset of n? And so this is going to be true. Why? Because if you take n, let x be an element of m, we want to prove that that is an n. But if x is a element of m, by definition, step number 1, or actually x, right? X is equals 4k for some k that belongs to the integers. But notice that we can see this as x is twice 2k, right? And I can see this 2k as some s. So k is 2s for s equals 2k that belongs to the integers. Okay? So that will mean that x belongs to m, to the set n. And so this that I just proved here, I took an element of m and I can see it as an element of n, means that n is a subset of n. Now we want to look the other way around. Is n a subset of m? And the answer is no. And so we have a counterexample here. 2 belongs to n, clearly. 2 times 1, right? 2 is equals 2 times 1. But 2 is not, it cannot be expressed as a 4 times k with k integer, of course. You take a rational, maybe, but not with an integer. So 2 belongs to n, but 2 does not belong to m. And this is something that you want to keep clear, because you're going to be doing this type of exercise. You're going to be looking for elements that are in a set, but they're not in the other set. Now let's prove that if A is in B and B is in C, then A is a subset of C. And so once again, this is going to be a proof. So if A is a subset of B and B is a subset of C, right? Then if F belongs to A, then X belongs to B. And this is by A being a subset of B. But if X belongs to B, then X belongs to C by B being a subset of C. Okay? So now the conclusion is, well, then if X belongs to A, then X belongs to C. And so that implies that is equivalent to A being a subset of C. Notice that I'm following still the 5 steps of the proof. This is my step number 1, definition of the proof. This is my step number. This is my assumption, and definition of the assumption is this second step. Then here we have our manipulation, and we reach to definition of the conclusion. And then here we have our conclusion. Okay, so we're still following the 5-step structure for proofs here in sets. Okay, let's continue this in the second part.